Hello everyone, I welcome you all to this new session. In this lecture, I'm going to introduce the term process. Process is a very, you can say, abstract term which we use in operating system. And the general definition of process, it is given in your textbook like Galvin or any other book like Tannenbaum. The book says that process is a program in execution. Or more precisely, you can say process is an instance of a program in execution. Now, when we are saying process is a program in execution, that means there is a program associated to a process. Now, what is a program? And we all are quite familiar with languages like C, Java, C++, or assembly language. There are many. We can write programs. So, what are programs? Programs are set of instructions we write to perform some task, right? So, let's say if we want to print something, hello world on the screen, we can write the syntax by following the syntax of the language. If we are writing in C, then we write according to C, or if we are writing the hello world program in Java, then according to Java, and so on. So we write a program like that. If we want to add two numbers, then we can write the program of adding two numbers. So let's say like this, we can write a program. So let's say here there are two numbers and we are trying to get the sum of these two numbers. So first we are scanning two numbers, taking input from user, and then we are adding them and then printing, right? So this is a program. Now what happens, actually generally as a human we use high level language. High level language are languages, those are easily understandable by the human beings, but your chip or machine doesn't understand those languages easily. So we need to use some converter or language translators. So we use either compilers or interpreters. We convert the high level language to the low level language, right? Low level languages are very near to the machine or chip or hardware, whatever you consider, or your CPU, right? So high level language need to be converted into assembly code or machine code, right? So if I take the example, let's say if we convert this code into assembly code by using some translator, language translator, it depends upon the which assembly or the low level languages, they are dependent on the platform. So let's say if I consider x86 architecture, and if we convert this program will look like this. Now in this program, this is an assembly, there are different portions actually. So the portions which you can easily see here, one portion is maintaining the data, okay, then there is BSS portion, and there is another text portion, okay. So right now I am not discussing, like, you can understand what is data and what is BSS later on. Now let's discuss about the text, actually the actual code, right? So whatever the instructions we have written, those instructions are converted into text. So the text is containing, let's say, these number of lines, the line 1 2 3 4 5, and after this sixth line is here. Let's say this is comment, so this is sixth, seventh, eighth, ninth, 10th, 11th, 12th, 13th, 14th, 15th, 16th, 17th, 18th, right? So there are many number of lines, 21, 22, 23, 24, 25, let's say 26, 27, 28. Right? So there are many lines. Okay, so these are the lines, those are generated. So your 2-number addition program is converted into this number of instructions. As I have mentioned, program is nothing but set of instructions. We may be writing the instructions in high level language, but ultimately it is going to be converted into low level. So these are the instructions. Let's say 54 instructions has been generated and there is a program. Now what is the challenge as the CPU end? CPU fetches the data. The speed of CPU is fast. The speed of CPU is fast, right? So let's say I assume there is a CPU and CPU can execute or run one instruction at a time, right? So I'm saying this is CPU. Now CPU is having some associated registers. So you consider there are certain registers. One very important register is program counter. Another very important register which CPU frequently uses, that is instruction register. So I'm mentioning, let's say these are two registers. So I'm saying this is PC, program counter, and this is I'm saying instruction register, IR. Okay. You must be familiar with these two, program counter and instruction register. Your program which I have shown you, which is looking like this, or maybe in some machine level language also, your ultimate program is available. That program, the very first thing, need to be loaded inside the RAM. So let's say this is your RAM, and inside your RAM, those line of code will be loaded and will occupy some space. Now the point is how much space your program will be consuming inside the memory. So this is, I'm saying RAM, and here let's say operating system has been loaded. Okay. Now after operating system, let's say there is only single program, so we are loading this, and this size, let's say operating system is consuming something, so this size is, let's say, 5000. Okay. Now after this address 5000, we are going to load the program. Now we need to find out the size of the program. Program has a number of things need to be loaded. The very prerequisite thing, the code which need to be executed. Okay, because process is a program in execution, and ultimately we are executing the instructions one by one, right? So if I consider x86 architecture, generally there are two types of instructions supported: variable length instruction and fixed length. So if we consider fixed length of instruction, these instructions are generally of 2 bytes, means 16 bits. Now if there are, assume that 54 instructions, then the total program size, so if I am saying the program size here will be 54 into 2 byte. So that means your text section, which is containing the code, it will be 108 byte. Okay, so at least 108 byte will be required inside the memory. So let's say text we are loading from somewhere, from this place to this place, and this portion I'm assuming that this is actually 108 byte, the length of this, and because it was started from 5000, so it will become 5108, that this address, right? I hope this is easy to understand. Now the thing is, all the instructions, those are like 54 instructions. You may number from 0 number of instruction, so I am writing I0, then it will occupy the next address I1 dot dot dot, and then let's say I53 instruction, right? Now what happens when the process is executing? Okay, these instructions are getting executed by the CPU. So the very first address will be loaded in the program counter. What is program counter? Program counter stores the address of an instructions need to be executed next. Okay, program counter. So PC I'm writing here, program counter, PC, program counter. And what is IR? IR is instruction register. These both are registers only. Program counter stores the address of, it stores the address of next instruction. To be executed, and it stores the instruction, which is currently being executed. So instruction register stores the instruction which is currently being executed, and what instruction need to be executed next, their exist, or you can say memory address, will be stored in PC. So let's say this is starting, or the very first instruction is loaded inside the IR. So this IR is having the very first instruction. Let's assume that the very first instruction I'm saying move, MOV EEX4, right? So that is loaded here. That MOV instruction is loaded here, and it is getting executed. The next address, because the first instruction was available at 5000 address, and every instruction is having of 2 byte, and RAM is byte addressable. So I'm writing here RAM is byte addressable memory. So the address in PC at this point in time when this very first instruction is executed, that will be 5000 plus 2, so that is 5002. Once this, the very first instruction I am saying, let's say I0, will finish its execution, from this address which is available here somewhere in the memory, the instruction I1 will be fetched and will be loaded in IR. Then CPU will start executing, and then the next thing will happen, and it will keep on happening again and again. And this is execution of process, right? So come back to the point. What is a process? Process is a program in execution, and whole lot of things, or these things I have elaborated so that you can understand when I'm saying program in execution, what is the meaning of execution, right? So the execution of the program, one by one instructions are getting loaded inside the registers, or you can say IR, and the CPU is operating on those instructions. But when CPU start operating on those instructions, CPU requires some other things also apart from the instructions, like data, right? Because instruction having two parts. Every instruction has two parts. One is opcode. So if I am saying instruction has two parts. One is opcode, another is operands. Okay, so you will study all these things in detail in computer organization and architecture. You may be familiar with opcode and operands. Operands actually the data required to operate the opcode, right? So if you are saying move, what to move, that data need to be decided. So that is the operand. Okay, so move is the opcode. So I'm writing here opcode, operational code on which your CPU can act, right? Now when the process is executing, because in system there is not only the single process, we are using multi-user multitasking, or you can say multi-programmed operating system. There can be multiple processes. So you assume one scenario. Let's say you are doing some job, some task in your office, or maybe in your home or kitchen somewhere. We assume that a lady is working in kitchen and she is doing a number of things, or maybe two things in parallel. So she is cooking something, let's say making a tea or coffee, and then she is also doing some other thing in parallel. She is preparing some other dish. Both the dishes, when she is preparing, both the dishes are having some number of steps. So this one is having a number of steps, and to prepare dish 2 is also having n number of steps, right? And these steps we are considering the program. So when C is preparing one dish, it is process 1, and another dish preparation is process 2, right? Now, if CPU is only 1, let's say there is only one gas or something, you assume that, then the process need to be switched in between. That we consider as context switch. So one recipe is being prepared, one dish is being prepared. So let's say 1 step, 2 step, and 3 steps has been done, but there are further steps remaining of dish 1. Then the lady switch to the another dish and try to follow some of these steps of another dish so that parallelly both can be prepared, right? Now the thing is, when these things will happen, like process 1 to process 2, CPU will switch its control. What happens to process 1? The process 1 need to be preserved somewhere. Somewhere means in the memory, and the memory we are talking about RAM. So inside the RAM there has to be a data structure created which stores all the required information of the process, right? So let's look at what is the structure of a process. If I say the process description, you can say process look like this in a memory, and when we switch the control or CPU control from one process to another, we need to maintain some of the data or information. So every process have a code block and every process have a data block, right? Apart from code block and data block, there are two things also available. So process have one dynamically allocated memory that we consider as stack, and process has a data structure associated to it that we consider as PCB. So I'm writing here PCB. PCB is process control block. Okay, so I write here PCB, process control block. Okay, PCB stores almost every possible information about a process, like process ID, like process state, like the number of files opened by the process, like the pointers which is allocated to the process, like file descriptor, and number of things are maintained inside the process or process control block PCB. Then we are having a stack. We will discuss in detail when the stack will be created, but the stack will be maintained. Generally, the stack is created inside the RAM when a function is being called. So for every function call, there will be an entry in the stack, right? And then we have data block. So let's say I'm writing here data, and we have, let's say, code block. Okay, right? So all these things for every process will be maintained. Is that okay? Now there are certain things. These two things will set the context of the process. Context means exactly what has happened, how many instructions has been executed, what was the last executed instruction, in case context switching happens, all number of things will be there. So with the help of stack and PCB, the context of the process can be preserved, right? So this we consider as the context. Now what is the data and what is the code? So code, actually it is the actual program or set of instructions. Those are loaded inside the memory, as I told you in the previous case, like assembly code. So that is the code. So I say that this is program or instruction of program. Now what is data? Required data to execute the program or to operate on the code. Required data to execute the instructions, the program instructions. Okay, right? So it is that particular section. So you can remember this. There is process control block. Every process will have a process control block. And process control block, it is a data structure. So I write data structure. And data structures we create in RAM or primary memory. So it will be created in memory. The stack will also be created inside the primary memory. Data and code, everything will be loaded inside the primary memory. Okay. And this overall address space or address is allocated to a process where all these things are loaded. That is considered as process address space. So I'm writing one term, address space of the process. Okay. Address space. So please do remember, this is important term. When we discuss the memory management, then we will discuss address space in detail, right? So this is the overall picture of a process and the process execution. Let's quickly look at the process control block. So process control block typically contains a number of things. Like process control block has the very first thing, the process state. In next lecture, I will discuss there are 5 states of the process: new, ready, running, waiting, and termination. So for the time being, you just understand there are 5 process states generally given in the books. It depends upon the implementation. Actually, it is not necessarily 5. It depends upon, but you consider there are 5 because it is given in your textbook which you are following. Then process identification number, that is PID. It is also available inside the process control block. Program counter, as I told you, program counter which stores the address of instruction which need to be executed next. And CPU register like IR, instruction register, or other registers maybe. Then it also stores memory management related information like memory management, like which address is allocated, address space, another thing, the initial address which is allocated to the process. Then some accounting information like it is about the creation time of the process, right? The amount of CPU time it has already used and its current priority, etc, etc. There are different information which we consider as the counting information. And then IO status information, right? Include the list of IO devices currently being used by the process. So all these things are available in process control block. So process, although it is a very abstract and small terms, but it is a big thing itself. If you can understand process properly, you can understand operating system, right? So with this description, I am closing this session. I hope the process and execution of process is clear. In next class, we can talk about different states of the process and process transition diagram. Okay, thank you everyone for connecting. See you in the next class.